So you're then going to use v dv equals a dx, where we now have L minus x here of length on the rough surface, and the part hanging over the edge is length x. So what you need to do is to write an acceleration expression. You have to form an acceleration expression by writing the sum of forces x equals the mass times the acceleration in that x direction. And this sum of forces is going to be the weight of this hanging piece, the weight of the hanging piece, and I'm going to go ahead and help you with that. Rho g x is the weight. Okay, so we have rho g x, and then we have an opposing, this is all x motion. It's all x motion. So there's an opposing force here, which is that mu normal, which is going to be mu, and the normal is the weight of this piece of length L minus x, and that's going to be rho g L minus x times mu, and that's opposing this rho gx force. Mu rho g L minus x, and that's got to be equal to the mass that's being accelerated. How much mass is being accelerated? How much mass? The whole thing. The whole thing has a mass of rho, what? L. Rho L times AX. That gives you an expression in terms of variable x that then goes up into here. And then you're going to integrate from, what's x starting at? B until we let the entire chain sweep over the edge, and it's just the last link of the chain has just left the friction surface here. And so then you're integrating over here from 0, which correspond to right when it breaks loose, with B hanging over the edge, until you get your final velocity there. Okay? So I helped you quite a bit on that. But most of you probably would have gotten stumped by that first part, which is how much has to be there in the first place to be able to get the thing started.
Yeah. What I was missing was the rho part, having the mass density. I didn't even think about that when I was trying to solve it. So.
And that'll drop out. That'll drop out.
I forgot to accelerate the entire chain.
Yeah. Yep. That's what you forgot to? Okay. You only accelerated part of the chain. Yeah. And left the other part sitting there. Okay. Something like that. Yeah. Okay. Yeah. Now, in the curvilinear problems, let me see if there's some other homework problems here, first of all, before we move on, where I need to provide you with an answer. I think I've given you most of them, at least up to a reasonable level here. Okay, so the exam will cover up through, I believe it's this material in chapter 3 here. So the exam will be next Monday, a week from today, instead of Thursday. I was hoping to have it this Thursday, but I'm going to just wait until next Monday. Gives you a few extra days to get caught up on homework, etc. And I'm looking here. Yes, it'll be up through assignment 11. So plan on bringing your notebook with you next Monday with all your homework in order, And then that cover sheet, make sure you have the cover sheet with a single line marking off the problems that you've completed. And come see me for help if you need help on problems that you've been stuck on. Okay. Any questions? That stuff? Oh yes, chapter 2 you said you wanted to go back to.
218 and 220.
Okay.
Just a real quick question. Are we going to have the exam in here or in
No, we'll meet next Monday. We'll meet back over in room 206.
drill 6?
And I'll let you know, I'll confirm that on Thursday, make sure that room's still available.
Okay.
And now back to your question, Julie. Problem
218 and 220.
218 and 220, back in the earlier material. Okay. The answer to this mass is vertical velocity is 1.5 meters per second upward. 1.5 meters per second upward. Now, I'm not sure if that can, I think that shows up okay on the image. I labeled this L, I call this L sub, my notation there is screwy because it doesn't relate properly. What I want to show you is an alternative way that I talked with Pamela and who else was it? Yeah. What was your name again? Greg, yeah. Earlier today about this problem. And I showed him one way to do it. And there's actually an easier way that I think might be useful to you. So ignore my labeling that I put on that because I didn't do it properly. This is a 2 degree of freedom system. And I'm going to have to get my book. Something like this. Call this B, call this A. So the system looks like this, with this mass hanging. And the question is, what's the upward velocity given that each of these cables are pulling outward at 2 meters per second? This would be the same thing as if we had a drum, could be a spooled up drum sitting over here, on which this cable was then wrapping up with some omega. Same thing over here. Okay? So how do you handle that? Well, you've got two cables. So we could write a length equation, L sub B, for this one, which is made up of, and we're going to have to define some length here. Why don't we call this Y sub B? And over here, there's a separate cable, so we have 2 degrees of freedom, as I mentioned. And then if we call this distance Y sub A, then this distance between these two is also changing, contracting in here. So we have to label that distance Y sub B minus Y sub A. And now we write the equation like we've done previously for this left-hand cable. L sub B is made up of 2 segments of Y sub B. No, I'm sorry, 1 segment of Y sub B. And a segment of y sub b minus y sub a. Pamela, does this agree with the notes that we have earlier? Okay. So there's that equation. Now, when you differentiate that, here's the easier way to do it than the way I explained it earlier to you guys. If you differentiate this, this isn't 0 because this length is allowed to change. So this is LB dot equals 2YB dot minus YA dot. And this is equal to 2. And you come over to the other side and do the same thing. Come over to the other side and do the same thing. So you have this cable length, LA, is equal to 2YA plus, oops, that's it, I think, plus C. I forgot to put my C's on there. And then you differentiate this, and you have an LYA dot, which is not 0, is equal to 2YA dot. And so then you can substitute for YA dot back over into here, and then go ahead and put your 2's in appropriately, and you should come up with an answer for YB dot, which should be a negative 1.5. Okay, so this is a little simpler way for you to tackle it than the way I talked to you guys about it earlier today. Daniel?
Is it possible to solve the problem by looking at the total length of cable in the problem as opposed to the individual sides?
Not that I've ever done. I've never done these that way.
Okay.
I would have to write separate equations for each cable. Okay. If you can do it, let me know. I'd like to see it. The way I've always done these is do it the way I've described it, or do it through differential rotations. Differential rotations in the pulleys.
So is it the sum of the two velocities? YA plus YB is going to give you the velocity of the mass?
No, the velocity of the mass is YB because it's on that one core.
It's this chord here, YB dot. See this pulley right here. That's what's dictating the motion, right? So the answer you're going to get is minus 1.5 for YB dot. Negative because Y is defined downward. Correct. Okay. Do you have another one in that chapter, Julie?
Yeah, 220.
Okay. Just to show people that one. Here's the answer for it. And you can see the velocity of A is a function of the velocity of B.
Is that y squared plus b squared or the bottom?
Yes, y squared plus b squared, letter B. And B is, little b is half the separation distance between the pulleys up here at the top.
Have a negative in there? Does that make sense? Because if one's going to go up and the other's got to go down.
If you define both those distances as downward, or excuse me, if you define y as positive directed downward, and if you define YA as defined as pointing downward, then the motion of one, let's see.
Yeah, if you define them both downwards, then one of them have to be negative.
Yeah, one will have to turn out to be negative. That should show up in the solution. I don't know why I don't have it written down here.
It's saying define the downward velocity in terms of the other ones. Just define one upward velocity in terms of the other one's downward velocity, so there's two magnitudes.
Okay.
So then it would be
Yeah. And once again, you got to be careful to read the wording there. Determine the upward velocity of A in terms of the downward velocity of B.
Yeah. Are we assuming that the thing is hanging right in the center of that triangle?
That's a little pulley there. It's a little pulley in the center. So that's going to keep it in equilibrium because if you've got equal tensions as in different, let's see, if it's at different angles here and you got a pulley sitting there in the middle, then that pulley is going to allow the object to just always remain right in the center between that span 2B. It'll always just roll right in there, assuming there's no friction in that little pulley. Okay, that take care of chapter 2 questions? Good. Okay, let's go back over now to chapter 3 and continue doing some more problems with curvilinear motion. And the first one I thought would be good to tackle today is number 53 right here. I love to ski. I don't jump much anymore. I kind of. Oh yeah. And then, you know, after you do a number of different face plants and other sorts of geometric projectile motion with your body, start to become a little more cautious with it.
That first time's got to be the hardest.
Oh yeah. It's a real thrill though. But anyway, this is kind of a nice little problem. Now, I never did that. Who was that British guy in the last Winter Olympic? Or was it the last Winter Olympics or a couple of Winter Olympics ago? He was great. The flying, they had a name for him.
Eddie the Eagle?
Huh?
Eddie the Eagle?
Eddie the Eagle.
Yeah.
If you ever get the chance to find him on the video, that was amazing. And I don't know if you've ever, I was up in Norway years ago right out of college, and in the summertime, and I climbed up to the top of where they have the Olympic type of ski jumping, and they don't use it in the summer, obviously, no snow. But it's pretty impressive looking down and then the distances that those guys end up traveling through the air. But anyway, if you ever get a chance to go to some ski jump facility, you might enjoy doing that, to take a look at it. Talk about projectile motion. Here we have a skier coming down, traveling pretty fast, 180-pound skier, about my size, 80 feet per second, traveling at 80 feet per second, which is almost 60 miles an hour. 88 feet per second is 60 miles an hour. So that's pretty fast. And the lip is at 30 degrees to the horizontal. And what we want to figure out just before liftoff is what that normal force is exerted by the skier against the ramp, or the ramp against the skier. Okay? So it's a pretty simple problem. All you have to do is write your equation of motion. They didn't specify a particular coordinate system to use. But we have the skier at 80 feet per second lifting off at 30 degrees to the horizontal. And so the normal force by the ramp is at that angle perpendicular to the 80 feet per second, right? And so we could use XY coordinates, rectangular, we could use polar, we could use normal tangential. Your choice. What do you want to do? Ian suggested normal tangential.
Well, it looks like there's a constant radius as it's approaching that lip. So
Ah,
I think it would be easier to use the normal tangential.
okay, so we have a radius of curvature. I guess we probably might know that from the design of the ramp. Okay? So might be best, as you said, to use the normal tangential. Now again, towards the center of curvature is our unit normal. And tangential, remember, is always in the direction of the velocity. So we put those on our figure and write our Newton's second law equations based on that orthogonal pair. And so off of the vertical, if the velocity and unit tangent are 30 degrees to the horizontal, then that means that off of the vertical, the normal is going to be that same angle. So what we could do then is write our equations. If we sum the forces in the normal direction, must equal the mass times the acceleration normal. So we have N, capital N, positive in that direction. And then this is orthogonal to that. Must equal the mass times the normal acceleration. Am I missing anything? What's missing on my free body? When I start writing this equation, I've got my mass over here and my normal acceleration, which we know is v squared over that radius of curvature. But something's fishy there. I mean, we know the mass, we know the speed and the radius of curvature. The body weight. So I failed to include the weight of the skier, mg. So notice that there's a component of the weight that is opposing the normal. mg cosine the adjacent side of 30 degrees. So mg cosine. So we have to include that. That has to equal the mass times the normal acceleration. So we solve this for the normal force, and we get mg cosine 30 degrees, and we could go ahead and replace that with our 180 pounds. And we add to that the mass, which is the 180 pounds over 32.2. And our speed was 80 feet per second. And our radius of curvature is 150. Now, what I want to point out to you, the reason this is a very elementary problem. Right, very simple. What I want to point out to you is these approximate values here. And I wrote them down in the book. $155.9. I'm going to go ahead and move my book. $156, and the other one, the dynamic force there, due to the motion, is 338.5 pounds. For a total of, actually I wrote that wrong, 238. Don't have my glasses on. And for a total answer of 394. This is the component of the skier's body weight exerted normal to the incline, right here. And that's the mass times acceleration due to the motion. And you've got to be, you know, that's reasonable. I mean, you could do that if you're in pretty good shape, be able to handle that. Kind of like sort of instantly bench pressing that much weight, okay? But I don't know if I've seen this before, where all of a sudden a skier or a snowboarder goes into a really tight curve, and you know what happens? They just collapse. Their legs just collapse, man. They just go right down, and sometimes you end up with knee injuries or ankle injuries, and it just go down and squash right into the snow because there's too much force there. They just couldn't handle it.
Wouldn't be instantaneously benching 394. Be constantly benching 238. And then
Speak up a little bit, please.
It wouldn't be instantaneously benching 394. It'd be constantly benching 238.
Yeah.
With the 156 slowly being added on.
And what happens, that's true, this would be, well, actually, this would be
Actually slowly
greater.
being taken
This
away.
would be up as it comes through the flat, this goes to 180 on the flat. And then up in here, it's different. But it depends on the curvature. Now, what's going to happen, what's the skier going to experience as soon as they leave this point? All of a sudden, that acceleration, all of a sudden, that piece of force disappears. And let me give you a, if you don't ski or snowboard, let me give you an example, because most of you either ride bikes or drive cars or motorcycles.